See, the main content of those lectures was understanding how to couple through what is called minimal coupling. That is, the minimal coupling is J dot A. So, review of the old lecture of 19 and 20, right? So, what you want to do is to write a J dot A interaction or a J dot B interaction or a J dot WA interaction. This is what we have done, right? JA dot WA. And in each case, we have identified what the J's are, right? And we get the J. So, how do we get the J? So, we have a Lagrangian. You ask for global invariance under, so this will be U1 electromagnetic, the first one. The second one is U1 hypercharge, and the third one is SU2 left, right? Then you get a conserved current. That is for the global invariance. Then you ask for local invariance under all these things. Okay, and what do you get? You get the minimal coupling, this as I wrote above, and that gives you the definition of d mu. Then we showed that, so we get the so there are some subsections of this. So we get W prime from the requirement that d prime u is equal to ud. Then we get G mu nu from d mu d nu is equal to Ig sigma a by 2 W mu a. Sorry, not W mu a, G mu nu a, sorry. That was the content of the course, right? Everything is clear? Yeah. So, by the way, only this one, I think some of you were a little confused when I said that you could drop the higher order term. So, what I have done is that some problem was there with the scanner. I'll put this on Slack. So, I'll do the whole calculation without making that approximation and show that you get the same answer, because you can explicitly see the higher order terms dropping out. Okay. You people went into breakout classrooms and did this, right? But we dropped some term saying it is potentially a higher order term, and some people were confused. So I have actually calculated it. I was trying to scan it, but there was some problem. So I'll scan it after the class and I'll put it up on Slack. Okay, so you can actually do this exactly without making any approximations, strictly keeping terms up to order theta and dropping theta squared terms. Okay, so this was the content of the earlier classes. So is this all clear? Then the final thing we did was, once we did the coupling, so once we did the coupling, we explicitly showed that off diagonal terms, interaction terms, give the usual Fermi theory of charged weak interactions, right? Then for the diagonal piece, we wrote BW3 in terms of AZ using an angle which is the Weinberg angle theta W. Sorry?
Ma'am, Krishna is asking something.
Oh, I heard some noises. Krishna, can you please repeat?
What is written under minimal coupling d mu? Like, why is not clear?
Minimal coupling d mu. Minimal coupling gives the definition for covariant derivative d mu, and from there, from that definition of the covariant derivative and the transformation property required of the covariant derivative, which will leave L invariant, right? That is d prime u is equal to ud, where this is local invariance under the transformation, some u, right? U either belongs to u1 or SU2, depending on which theory we are taking, right?
What is the symbol, the first symbol that is?
W mu prime from d prime u is equal to ud. This is W mu prime. Yeah, so we got I don't remember the signs. W mu prime A is W mu A minus 1 by G d mu theta A, which was the same as the QED part, and then we got an extra portion, right? Plus or minus G epsilon ABC theta B WC, right? So this is the definition. Then we got G mu nu from this definition, and then we have the entire Lagrangian now, and then we looked at the off diagonal terms. We got completely charged current weak interactions, which is V minus A theory, right? V minus A theory or Fermi theory or the usual theory of weak interactions. And the diagonal pieces we rewrote because we needed two things. We needed an electromagnetic field, which we did not yet have, and we needed that W plus W minus, which is here, the off diagonal element show W plus W minus, the charge currents, that they have to interact with the A field. They will do that through the interaction with the SU2 components of W3, and therefore we rewrote this in terms of cos theta A plus sin theta Z and so on. And then we got the interaction with the electromagnetic field, and I did not show you the interaction with the Z field because it is more complicated. It is neither pure V minus A nor pure V. It will be some form which is, so Z interaction will come out to be gamma mu into A plus B gamma phi, and the A interaction will come out to be exactly gamma mu into charge of the particle. Is it clear? I mean, I've dropped I and so on. I mean, all that is there. I mean, some G will be here, some G will be there, some Q will be there, but basically this is pure vector. The W interaction is G gamma mu into 1 minus gamma phi. So pure V minus A, and this is mix. So did anyone try actually looking at what the Z interactions are? But in any case, I mean, you understood, right? You understood how to get the interaction with the A, and that gave you this gave you the relationship G sin theta W is equal to G prime cos theta W. So the tan theta W is G prime by G. And also we used the fact that the hypercharges were obtained using Q is equal to I3 plus Y by 2. So this is a summary of the last two classes. Is it okay? Is everybody clear about every part of this? Because this is the heart of the interaction. What we have done is, you take the electromagnetic interaction that we studied, you take the weak interaction that we have studied, take all their properties, and we find that this kind of coupling actually reproduces the correct interactions of all the particles with all the interacting mediators, that is the Z, the W, and of course the newly predicted neutral Z boson, okay, apart from the photon and the W. So all that we have missing now are the mass terms. We showed that the current conservation here, conserved current, and we found only if m is equal to 0 for the SU2 case, right? So now we have to correct that. We know that all these particles have mass except the photon, and therefore we have to somehow incorporate the masses without spoiling all these nice invariances and symmetries that we have obtained, which describe the various interactions. So today's class, if everything is clear now, I will move on. So what we are going to now look at is spontaneous symmetry breaking. And mass generation through Higgs mechanism. There are many people, not all of whom got the Nobel Prize, but this is called Higgs mechanism. So there are many other researchers involved in these discoveries.
Will you be teaching a strong interaction in this course?
No, I will not teach strong interaction, but you can write strong interaction. What will you write? What is strong interaction? You have to write covariant derivative d mu a. That's all. That's all. That's all. Okay. Only thing is that the trace calculation will be much harder because you people, it was very nice that in college you learned all about poly sigma matrices. I didn't have to teach you that. You were very comfortable. So when I write sigma plus sigma minus sigma 3 and eigenvalues, you are familiar with all of them. You're not familiar with the lambda matrices. So the traces are a little more complicated. The SU3 is a little more complicated group than the SU2, but the whole technique and mechanisms are exactly identical. Okay, there is absolutely no difference. So what you will have is, apart from tracing over the gamma matrices, you will have to trace over the color factors, color indices, the A. Okay, and there are trace theorems for that as well, and you have to simply implement that correctly. If you're curious, you can do one calculation. You can do quark scattering and get the answer. It will be the same as take a quark 1, quark 2 scattering, so that they are different quarks, so that you have fewer diagrams, and it will be very similar to electron muon scattering with some additional quark color factors which actually factorize out. So it's simply a number multiplying the old cross section. Okay, kinematics will be identically the same, everything else will be the same. That's why I'm not showcasing that. There is nothing new to be learned. What is new to be learned, what is interesting to be learned in strong interactions is confinement and asymptotic freedom, which is well beyond the mandate of this course. Okay, so maybe in the next semester, I think Rahul Sinha will be teaching particle physics. Maybe he will tell you something about it at that time. Okay, so we come back here. So spontaneous symmetry breaking, sometimes called SSB, okay, or Higgs mechanism. So mass generation is through Higgs mechanism. So the first time you see spontaneous symmetry breaking, it's totally weird and you can't understand why on earth anyone actually ever came up with this idea. Okay, and the last time you see it, the same feeling remains. Okay, there is absolutely no way to understand the how and why of this mechanism. Okay, all you can say is what it does. It gives masses. It's a totally bizarre and weird mechanism. So you hold off your questions about why and how. So I will do three things and I will show you what it does. I will show you that it can give masses to gauge bosons. And that is really what the strength of this theory is. Towards the end, I will make some remarks about why on earth you would want to do such a thing or why you would want to believe it anyway. But let me start out by telling you what I will do in this class. First, I will take a simple Lagrangian and look at a U1 global, not a local invariance, but a global invariance, okay, and look at this with a U1 discrete symmetry. Then I will look at, I will look at spontaneous symmetry breaking for such a Lagrangian. Then I will look at it for a global invariance, but for a continuous symmetry. And finally, I will look at the local gauge theory. Okay, so until I finish all this, it will seem, as I said, totally bizarre. So we just hold on to our incredulity and just watch. Okay, I mean that's my advice to you. It's truly bizarre phenomenon. Okay, so let's write a Lagrangian which has U1 global invariance. I want to take a discrete symmetry. So here I start out, for simplicity, I start out with a scalar theory which has a 5/4 interaction term. Have you done 5/4 theory in field theory?
No, we are doing means.
Okay, okay, you are doing.
We have not done it, but we have started in interactive field theory. I think.
Okay, fine, fine. So we will just write down then what the 5/4 theory is. Have you seen the? Okay, I did not explicitly show you the Klein-Gordon Lagrangian, but if I write it as this is a Lagrangian density. Remember we had earlier only the Lagrangian. So here I write half d mu phi minus half m squared phi squared. Does this look familiar? If you have not seen this, please write the Euler-Lagrange differential equations, equation of motion, and show that this gives you box plus m squared phi equal to 0, which is the usual Klein-Gordon equation, right? Right? Have you not seen this at all in the field theory course?
We have seen
Yes,
this.
ma'am, we have done.
Ah, you have seen this.
Klein-Gordon.
You have seen this. Now this is a free field theory. Now I am going to add a 5/4 potential term, and for this coupling constant is called lambda. It's standardly called lambda, and this 4 factorial is there just because when you have a 5/4 interaction, many times that 4 factorial is convenient and the terms cancel so that you don't have to keep track of factors in the denominator. That's why they have divided by 4 factorial. So if I write the Lagrangian as the kinetic energy minus the potential energy, then my potential energy is half m squared phi squared plus lambda by 4 factorial phi power 4. Now let me plot this potential. So first of all, yeah,
M square.
yeah, thank you. Okay, so first of all, lambda greater than 0. Why should lambda be greater than 0? Let me plot this potential. So this is V of I as a function of I. Okay, so if I didn't have a mass term, this is the 5/4 potential, right? And if lambda is positive, this means that I have a bounded potential, right? If lambda is less than 0, then the potential is unbounded. So my lambda has to be greater than 0. Now, so the large phi behavior is completely determined by the lambda term. And now I just complete it for this. So this is my potential. Okay. However, for certain reasons which as I said will be totally bizarre, so lambda is greater than 0, and normally I would say that m squared is greater than 0. If m squared is greater than 0, this is the usual Klein-Gordon particle, scalar particle with this potential, right? However, you take m squared to be less than 0. Then you can see that the minimum of the potential is not at phi equal to 0, but the minimum of the potential comes as when you take, I am going to stop writing script V because it is very hard to do it on the board. So I am going to write dV by d phi is equal to 0 is equal to m squared phi. So you can see that 4 factorial 4 cancels, so it will be lambda by 3 factorial, 3 factorial is 6 phi cubed, or phi into m squared plus so phi equal to 0 is still a solution, but the other solution is m squared plus lambda phi squared by 6 is equal to 0, or phi squared is equal to minus 6 m squared. So let me write it here, phi squared is equal to minus 6 m squared by lambda, right? So you can see that at large values of phi, of course this term will dominate, so they will match at large values of phi, but the minimum now is at these 2 points. This is phi squared is equal to minus 6 m squared by lambda, or phi is equal to plus or minus square root of this quantity. And since m squared equal to 0, this is a positive quantity and this has 2 solutions, 2 discrete solutions, 2 discrete solutions. Up till here okay? So what does it mean that we have done such a thing? Yeah?
Isn't phi imaginary?
Phi, no, which phi? Phi can be complex, but phi squared is, But this is just a, this is not a, this is just a scalar field, right? Phi is real. So let me put it very clearly. So phi real.
Yeah, that was what I was asking.
Yeah. So phi can be complex. We will come to it in the next phase, right?
Here it is a scalar real field, right?
Yes, real scalar
So
field.
when we take the square root of minus 6 m square by lambda, then
Yeah, but m squared is less than 0, right? So minus 6 m squared is positive.
we are considering only the less than 0 case, right?
Sorry?
So m square is less than 0.
When m squared is greater than 0, there is nothing to write about. It is the usual Klein-Gordon particle in this strange potential, 5/4 potential, right? But if m squared is less than 0, there are two solutions. In fact, phi is equal to 0 as a solution, but it's a local maxima, it's not the minimum. The minimum is sitting at this. Phi is equal to plus or minus square root of minus 6 m squared by lambda. Phi is real, but phi can be positive or phi can be negative. It is symmetric, right? Please remember, V of minus phi is equal to V of phi, right? It's symmetric. It's a symmetric potential. Both of them are symmetric potential. That's because the potential is a function of phi squared and phi fourth, even powers of phi, and not a function of odd powers of phi. So it's a symmetric potential, and phi is real, but it can have positive and negative values, and these are the positive and negative values. And minus 6 m squared is positive because I have considered the case when m squared is less than 0.
Like we say m square is less than 0. What do it actually signify?
Yes, that's what I'm saying.
And we can.
I told you that's exactly why I told you in the beginning that you hold all your questions about this. There will be, in fact, in the end, no answer to this question. You can say a lot of words, but the fact is that when we do this, the thing works and you can get masses for these particles. Okay, it's a very, very big question mark. And I said I will make a few remarks, but they are all hand waving remarks. The what you mean by this negative, we will also understand it as how we define a dynamical field. That I will answer immediately. Okay. So obviously, as you point out, I mean, why he thought of such a thing or why they thought of such a thing, I really don't know. But obviously, when you have mass squared less than 0, this is not a physical field. That means that the way the Lagrangian has been written is not in terms of the dynamical fields, and we will immediately answer this question. Therefore, what are the dynamical fields? So, for that we first understand few things. Suppose I now transform this phi by some u1 transformation, global u1 transformation. The Lagrangian is invariant under that global u1 transformation. But however, you can see that what do you mean by the lowest potential energy value? We know that the Hamiltonian is equal to T plus V. Kinetic energy is the same. So when the potential is the smallest, that energy is the smallest, that's what the Hamiltonian represents, and therefore that is the ground state. So now I have two ground states because both of them will correspond to the same Hamiltonian, but I am not allowed to do this. If you remember what I said when we went back to radioactivity and decay, right, and line broadening, I said the ground state has to be unique, because if that line broadening means that there is decay, but that cannot be the ground state. So I cannot have both of them as ground state, so I have to choose one of them. So let me write that equation down. Phi squared is equal to let me write phi is equal to plus or minus square root of minus 6 m squared by lambda, and let me choose the ground state to be phi, and let me call that value v or phi naught, maybe some constant. Phi naught is equal to plus square root of minus 6 m squared. So I am choosing this to be the ground state, and this is not the ground state. But you can see immediately that this invariance, the u1 invariance, is lost because now this symmetry has been broken by the ground state, although the Lagrangian still contains the u1 invariance. So what have I said? I apply a I apply a global u1 transformation. We all know how to do it. I don't want to write it again on phi. So phi goes to e to the I alpha times phi, and the Lagrangian is invariant, but this ground state breaks that invariance because I have chosen one of these two discrete minimum energy states to be the ground state. So let me keep going. So please note that is, I have got, let me finish this part, you can ask the question later. So I have got a spontaneous symmetry breaking by just choosing one of these as the ground state, and let us see what is the consequence of that. Yeah, ask the question.
Ma'am, when I'm not able to understand why after the part you said that choose ground state.
I have chosen the ground, I have not gone beyond that. I have chosen the ground state as plus of this quantity. That's all. Okay. So all I am saying, I am observing is that the Lagrangian is invariant under a global U1 transformation, but the ground state is not, because the U1 transformation will take this to this and this to this, but I have chosen this to be the ground state. So the ground state breaks the symmetry, whereas the Lagrangian, at the Lagrangian level, the symmetry is not broken, hence it is called spontaneous symmetry breaking. Now we still have to define or identify the correct dynamical fields. Why do we have to identify the correct dynamical fields? Because we know that it makes no sense to have a particle with mass squared less than 0, which means that the mass is an imaginary quantity, right? So we have to reconstruct this in terms of, let us identify the dynamical field to be phi tilde. And let me write phi tilde to be equal to phi naught plus minus phi. Let me do it the other way around. Let me write phi is equal to phi naught plus phi tilde, just to get the signs right. So if I ask what is the vacuum expectation value of this field, the vacuum expectation value of this field is the value in its ground state, which is the vacuum value, and therefore that is phi naught, right? Now what is the vacuum expectation value of the phi tilde field? Is equal to vacuum expectation value of the phi field minus the vacuum expectation value of the, but phi naught is a constant. So this is simply phi naught times 0 0, which is 1, and therefore this is 0. So what we are saying is that we have now chosen a dynamical field whose vacuum expectation value is 0 and not phi naught. So this is not the correct dynamical field, but this is the correct dynamical field. So let us put that back in this Lagrangian. So I am going to put it back in this Lagrangian and then see whether we can make sense of what this field actually means. So I am always going to be looking at m squared less than 0, please remember, okay. So what I am going to now write it is, let me write it in terms of the dynamical field. So phi is equal to phi naught plus phi tilde, right. So phi naught plus phi tilde, let me write just squared over here. There was a question? Yeah, I am going to keep writing, ask your question.
Then you are talking about the field as if it's a wave function. I mean, choosing the ground state when you write that phi is equal to phi naught is equal to some constant. So you are talking as if the field is no longer an operator but a wave function. Am I thinking it the right way?
It's,
or am I getting something wrong?
I can always ask, haven't you done vacuum expectation values of fields in field theory?
That I have done.
That's all. So this is a field, and I am asking what is the vacuum expectation value of this field?
No, but I'm talking about the ground state. When we say the ground state of an operator, field operator, isn't it always a vacuum state?
Yeah, but sorry, okay. I mean, I postponed this to the end of the lectures hoping that, the field theory course, they would have explained it. Okay, so, okay, let us pause this calculation. So what do we mean by a quantum field, right? So I have said in between words on what is a quantum field. So when we talk about this as a quantum field theory, now I have written this Lagrangian density as a quantum field theory, where phi's are now quantum fields and they have a mode expansion which includes both the creation and the annihilation operator, right. I have written the mode expansion for, I think, QED and the photon field and psi field earlier in some earlier class, okay. So that is what my field is now. I don't have a wave function, sorry, but I have a field. right. So this field theory now, as I said, has to include both scatterings as well as decay. So that means that if you look at the classical notion of a quantum field, in the sense of quantum mechanics, including relativistic quantum mechanics, we always had either phi star phi or phi dagger phi equal to 1, right, or 2e or whatever, so some normalization constant, right. This does not allow for decay, and therefore we go away from the notion of wave function and go to the notion of fields. And the way to look at it is this. Suppose I just look at this. So I have E plus E minus annihilating to photons. So I start out with a theory in which I have electrons and positrons. I end up with a theory which has photons. Of course, this is gamma star. It's not relevant to my argument. So that means I should be able to, in my theory, create and annihilate particles. So my vacuum state, which we call the ground state, is not the relativistic quantum mechanics vacuum state, which has nothing at all, but the vacuum is full of things, right? I mean, this, I hope you learnt it in field theory, right? This vacuum state contains anything that you want to generate. I can pop a E plus E minus pair out of it. I can pop anything out of it which has the quantum numbers of vacuum, right? So the ground state only means that I can have an infinity of particles, but I have a ground state which is the lowest energy state. I don't talk about vacuum as we thought of traditionally as having nothing at all. For example, in quantum mechanics, you can write this and then you have creation operators which generate all your 1 particle, 2 particle, n particle states, right? You don't have that anymore. There is nothing like zero state as being nothingness at all. It always contains any number of particles that you like with net quantum number 0. Is it clear? So that is my vacuum state. So I can always take this field and ask what is the, so the ground state of that is the lowest energy state. That's all we are saying. This field is always existing, right? See, you think of a particle, right? When you say in quantum mechanics there were 0 photons, there are 0 photons, but the field always exists. In field theory, the field always exists. So the ground state only corresponds to the lowest energy state, that we call the vacuum state. Okay, so vacuum doesn't mean nothingness anymore. It just means that it is the lowest energy state for that particular Lagrangian. So now we say that I had a wave function, I had a field phi which had a peculiar property of having an imaginary mass, and also you have a non-zero vacuum expectation value, here, and therefore it didn't have the proper required quantum mechanical properties of a ground state. So now what I do is I define a dynamical field which is phi tilde, which has now 0 vacuum expectation value, and the next we have to ask is, does it have a reasonable mass? Does it also have imaginary mass? Of course, we will find it has a reasonable mass, and that is what I am going to show you. Is it okay?
Yes.
Good. Now, let me now do this calculation. So, so you can see that d mu phi naught is 0, so this is simply d mu phi, right? I mean, the first term does not matter at all. So this is just d mu phi tilde, then minus half m squared, so phi naught squared plus 2 phi naught phi tilde plus phi tilde squared, and the last term is minus lambda by 4 factorial, this thing whole squared, right?
Ma'am,
Yeah?
can you told us about what is linear spontaneous relativistic?
No, I am not going there. I told you I am going to only do the derivation. I will make a few remarks in the end, okay? So it is a very bizarre thing. So there is, I can say many words, but ultimately it is bizarre, okay? So let me show you mathematically what is happening. Once we understand mathematically what is happening, then I can say a few words to try to understand it, okay? So this is phi squared, this I have expanded now, and this is phi fourth, which should be this whole squared, right? So I have to square this quantity and put it here. So let me square this quantity and put it here. So you can see that this is no phi field, I mean no phi tilde field, 1 phi tilde field, square phi tilde field. So I am keeping the order here also. So I am going to write phi naught power 4 plus, there will be, the square of this term will be 4 phi naught cube phi tilde. So it will be a linear term in phi tilde. Then when I square this, I will get 4 phi naught squared phi tilde squared. So, I will get a phi tilde squared term. Then the cross term of these two will also give you phi tilde squared. So, then let me write that down. So, 2 phi naught squared phi tilde squared. So, I have got square of this, cross term of these two, cross term of these two, square of this. Now, I am left with cross term of these two and square of this, which will be cube terms and quartic terms. I am not going to write them, they are just interaction terms. I am more interested in the terms up to phi tilde squared. So, let me write them down. So, this sits as it is. Now, I have some constant terms. So, here is my constant terms, half m squared phi naught squared from here and minus lambda by 24 phi naught power 4 from here. Then I have linear terms in phi. See, you would never have seen this before, right? Lagrangian has always quadratic minimum terms in phi. So, what is this linear term doing in phi? Let us write it down. So, the 2.5 will cancel. So, you get minus m squared phi naught from here, and there is another linear term over here. The 4 and the 4 factorial will give you 3 factorial, which is 6. So, minus lambda by 6. So, let me write an overall minus lambda by 6 phi naught cubed. Okay. Then let me write the phi tilde squared terms. So, I have got rid of this also. So, phi tilde square term is minus half m squared. Okay. Then here I have a 4 by 4 factorial is again 3 factorial. So, minus lambda by 3 factorial is 6 phi naught squared. And then I have one more term here, which is minus. So, this is 4 factorial is 24. So, 2 by 24 is 12 phi naught squared plus higher order terms. I am not going to write them. So, let me write this here, phi naught squared is equal to minus 6 m squared. This was our condition, if you remember. Okay. So, you can see that what is this term? If I take out a phi naught, this is 0, right? M squared is equal to minus lambda by 6. So, lambda is equal to minus 6 by m squared phi naught squared. So, this term is 0. So, that linear term in phi tilde, which you had no interpretation for, is actually 0. Now, let us look at the quadratic term. So, let me write it here somewhere. I do not want to rub out these values. So, I have minus half m squared minus, so let me write minus half outside and take the second term. So, it will be plus lambda by 6 phi naught squared. So, I have written the first and the last terms, and then I have a minus lambda by 6 phi naught squared. So, you can see that this is also 0, same thing, m squared plus lambda by 6 phi naught squared is 0. So, we know that lambda by 6 phi naught squared is minus m squared. So, this will be minus of minuses plus m squared phi naught squared. So, that my Lagrangian is, I am going to now take this off. So, this will be 0 and the phi tilde squared will be plus m squared phi naught squared, sorry, phi naught squared phi tilde squared plus higher order terms. Now, let us look at this. So, I am claiming that this is a good, nice, well behaved dynamical field. Sorry, I should have put this. Okay. This is the kinetic energy term. So, it is fine. What is this? This is simply a constant. Phi naught is a constant, right? M is a constant, lambda is a constant. Now, we know that the potential can always be shifted by any constant amount, it will never bother us, right? It is only the potential difference that is going to bother us. So, this will not appear in the Euler-Lagrange equation of motion, so we do not care about it. Then the linear term in phi tilde, so I should write phi tilde into 0, which would have been incomprehensible, has gone away. And in fact, we have a term, if you look at the Lagrangian, what is the mass now? If I write this as m squared, I will write it as 2m squared times half, because I know that the mass is, in the Lagrangian, the mass term should have been minus half m squared phi squared. So that means the mass, which I call capital M, of this dynamical field is now, if I take out a minus half, is minus 2m squared, and because m squared is negative, the mass of this dynamical field is a positive quantity. Is this clear? So what we have said is that I start with a Lagrangian, which looks like the Klein-Gordon Lagrangian, but then I say that its mass squared is negative. Then I say that because of that, I have a discrete symmetry, so that the Lagrangian, which was invariant under the global U1 transformation, the ground state is not invariant under that transformation. Then I rewrite it in terms of some dynamical field which has proper vanishing vacuum expectation value, and I get a proper Lagrangian in terms of the correct degrees of freedom, in which the mass of this field is actually minus 2m squared, which is a positive definite quantity. So we have just done some mathematical manipulation. I am still not going to interpret this. I am going to next break a continuous symmetry. This was a discrete symmetry because I had two solutions for phi. Next I am going to break a continuous symmetry, and last I will do a local gauge transformation, and only then I will make the interpretation for all this stuff that I am showing you on the board. But mathematically it is clear, right? No, those are interaction terms, though they are all there. So they will give you self-interaction terms between the phi's, right? So the phi cubed term will give you phi cubed like this, and the phi 4 term will give you interaction like this. But I am only interested in the masses right now. So in the entire next 2 lectures that follow, or 3 lectures that follow, I am only going to be interested in making sure there are some constants which I can throw away. Linear term has to be 0, and the square term contains the masses, and that's how I am going to get masses for these particles. Okay. Higher order terms are definitely there. They are definitely there. I have not thrown them away. I am just not interested in them. They will be, with some rearrangement, they will give you some interaction term, which will be defined in terms of phi tilde rather than the phi. But when you want to, ultimately when you want to do Higgs self interactions, then you better calculate all those terms. But right now for this part, I am not interested in calculating it. So that's all. So what we have got now is, yeah, ask.
What do you mean by discrete breaking?
I had 2 solutions for the ground state, right? Discrete, two of them, finitely many. Now I am going to go to a theory where I will have a continuous symmetry. I will have an infinite choice of ground states, and I will pick one of them. Okay, that is where the interest lies.
You are saying that you have theory with field phi now, and you broke it down into 2 fields, right?
No, I didn't break it down into 2 fields. I had a discrete symmetry because I have 2 possible choices of ground state, and I chose one. It's a discrete symmetry, which I broke, right? It is reflection symmetry, right? That under phi naught going to minus phi naught, that ground state is, that goes into a non-ground state, so the ground state is not symmetric under it, right? Now I will go to a continuous, again I will keep to U1, okay? I mean, ultimately I know I have to go to SU2, but let me just keep it to U1 for now. And I will still look at global invariance, okay, of the Lagrangian. I am not yet coming to local theory. So how will I look at a continuous symmetry? I will write a charged field. Again I will think of a scalar field, which is phi 1 plus I phi 2 by root 2, and the conjugate field will be phi dagger is phi 1 minus I phi 2 by root 2, and I will show you in a minute why it's a continuous thing. So let me write the Lagrangian. Lagrangian is half d mu phi 1, I will just write squared, plus half d mu phi 2 squared minus half m squared. They have the same mass, obviously, right, because they are conjugates. See, it's a charged particle, right? So any particle which is charged has a phi and phi dagger separate, minus half m squared phi 2 squared minus lambda by 4 factorial power 4, okay. So this can be written in compact notation as d mu phi dagger d mu phi. You can check this. What will happen is that There is a 1 by root 2, 1 by root 2 in each of them, which will give you this half term. Okay. Again, I can write the phi 1 squared and phi 2 squared as phi dagger phi, and again that 1 by root 2, 1 by root 2 will give that half that is required over here. And now there is a power 4, so I will get a 1 by root 2 to the power of 4, which is a 4. So I will get a 4 times divided by 4 factorial, so I will get a 3 factorial phi dagger phi whole square. So you can check this is just trivial algebra, okay. I have rewritten phi 1 and phi 2 in terms of the charge conjugates phi and phi dagger. Is it okay? Now you can see what this let me look only at the potential, because that is the interesting thing for me. No half, sorry, m squared phi dagger phi plus lambda by 3 factorial phi dagger phi whole square. So I can now ask what is the minimum of this potential. So you can now write this as half m squared phi 1 squared plus, so write it all in terms of phi squared phi 1 phi 2. So you know what you will get, right? It is just the coupling of phi 1 and phi 2 fields. So I will get phi 1 into m squared plus 6 plus lambda by 6 phi 1 squared is equal to 0, and if I do dv by d phi 2 equal to 0, I will get phi 2 into m squared plus lambda by 6 phi 2 squared is equal to 0. I mean, you can see that from here, no? Maybe I should just do it here where I have actually written the terms. So let me write only v. Okay, so you can see that, right? So when I differentiate this with phi 1 squared, I get m squared phi 1 here, m squared phi 1, and this term will just give you the lambda by 6 phi 1 squared. So it is the same as the earlier one. So I have again the same set of solutions. Either I have phi 1 phi 2 equal to 0 if m squared greater than 0, or I have m squared plus phi dagger phi, sorry, this is not phi 1 squared but phi dagger, let me write it down properly. Let me write it down here, sorry. Phi 1 into m squared plus lambda by 6 phi 1 squared plus phi 2 squared is equal to 0. So you can see it from, maybe I should have put that here, phi 1 squared plus phi 2 squared the whole squared, right. So let me just do dv by d phi 1 is equal to m squared phi 1 plus 2 lambda by 4 factorial phi 1 squared plus phi 2 squared into 2 phi 1, right. So which is m squared phi 1 plus 2 into 2 is 4 So that is what I have written, I am sorry, okay. And this will be the same thing. So you will have m squared plus lambda by 6 phi 1 squared plus phi 2 squared equal to 0 for m squared less than 0. So now let me draw the diagram. So I am very bad at this 3D diagrams. So let me just try to write. So this is phi 1, this is phi 2, and this is v of phi, or v of phi 1 phi 2. So if you had m squared greater than 0, you would have got just, right? And if I have m squared less than 0, then okay, I will try to draw something. See, these are continuous values of phi 1 and phi 2, right? So I hope you can see that This says phi 1 squared plus phi 2 squared is equal to minus 6 m squared by lambda, the same thing, and let me call this some v square. So phi 1 squared plus phi 2 squared is simply a circle, right? So this circle, I hope you can see this circle. Is it clear? Is it clear now that I have a continuous symmetry which I break by choosing one particular solution? So every one of these states over solutions over here is a minimum energy solution, right, corresponding to dV by d phi 1 or dV by d phi 2 equal to 0, and I pick any one of them. So let me again pick, so let me pick over here, let me pick that phi 1 squared is equal to v squared, phi 2 squared, so phi 1 0 squared, what do, okay. You remember I called that the minimum value, right? It's a choice. I could have chosen each one to be v squared by 2, v squared by 2. I could have chosen phi 1 is v squared, phi 2 is 0. I could have chosen phi 2 is 0, phi 1 is v squared. And in fact, as I said, I could have chosen any point on this circle. But I am going to choose this particular point. So I am going to take phi 1 to have the non-zero vacuum expectation value and phi 2 to have the zero vacuum expectation value, which means that I will write that phi tilde 1 is phi minus phi 1 0, which I will call v. Let me write maybe, and phi 2 tilde is equal to phi 2. Now I have to repeat this analysis and write the Lagrangian in terms of the dynamical fields phi 1 tilde and phi 2 tilde. So instead of writing all the terms, you can see again that the d mu phi terms will not be affected by a constant. I am only going to write the potential part. So it is equal to half, not no half, m squared phi dagger phi plus lambda by 3 factorial phi dagger phi whole square. So let me write all the terms. So v is equal to half m. What is phi 1 squared? Phi 1 is phi 1 tilde plus v. And phi 2 tilde is simply phi 2 tilde, they are the same, right? Plus phi 1 squared plus phi 2 squared, the whole square. So I have to now write this down. So now let me be smart. I will now collect first constants, linear terms, quadratic terms, and then the higher order terms. So let me write it as, I know that I will get a constant term from here, right, v squared. The cross term will give me the linear term in phi 1 tilde. So there will be a 2 phi 1 tilde v divided by 2, so this is just m squared v. Then I will have a phi 1 tilde squared term, which is simply half m squared. And then phi 2 tilde squared term, which will just come as half m squared. Now I will have to write all these terms. So what is this? So you see that I have to write this as v squared plus 2v phi 1 tilde plus phi 1 tilde squared plus phi 2 tilde squared. So the square of this will be a constant, right? Then the square of this will be a phi 1 tilde squared. So the square of this will be 4v squared divided by 4. So it will be, okay. Then the square of this is a phi 1 power 4. I am going to drop phi cubed and phi 4 terms. The square of this will also be phi 1, phi 2 power 4. I am going to drop that term. Now I have to take cross terms. The cross term of this will give me my, no, I have already put the cross term of this. Sorry, I already put the cross term of this. Then I have to put the cross term of these two. So that will be plus 2 lambda by 4 factorial v squared. Then the cross term of those two will be the identical term. Okay. So that is the cross term of these two. So I have finished the cross terms for v squared. I will take that off. Now I have to do the cross terms of these two. That will be a phi cube term. This will be a phi cube term. This will be a phi 4 term. So I am going to drop the rest. Okay. So let us just make sure that we have got all the terms. The linear terms, there will be a phi 1 tilde from here, that is here. There will be a linear term phi 1 tilde from this cross term, and that is here. And here there will be a phi 2 tilde square term, and so, okay. So 2 by 4 factorial is 1 by 12. 1 by 12. I am doing something wrong. This squared plus this squared. I did not do this squared term. There are two terms, right? Sorry, let me just write this term. So we have v power 4 plus this squared plus 4 v squared phi 1 tilde squared plus 4 v cubed phi 1 tilde. So these are all the square terms, right? And then this v squared into phi 1 squared will give me 2v squared phi 1 tilde squared. So let me just check. So v power 4 is here, v squared phi 1 tilde squared. So v squared phi 1 tilde squared, let me write it again. So lambda, sorry, I am sorry about this, 3 factorial v squared phi 1 tilde squared. Then the phi 1 tilde term has, so 4, this was 4 v cubed by 4 factorial phi 1 tilde, and this was plus 2 by 4 factorial v squared phi 1 squared. Okay, fine. I am sorry about that. Okay. So 3 factorial is 6. 3 factorial is 6. And if I take a half out, this is also 6. So you can see that this term is 0. M squared plus v squared by 6 is 0. Same m squared plus v squared by 6 lambda is 0. So only this term remains and only this term remains. So what do we get now? Plus, of course, higher order terms. So that is equal to half. So some constant k plus phi 1 tilde into 0 plus phi 1 tilde squared into this. So 2 by 4 factorial is lambda by 12. So again you get half. So lambda by 6 is m squared, right? V squared plus phi 1 tilde squared into 0 plus higher order, plus higher order terms. So what you can see now is that there is a constant term which, as we interpret, we do not care about because the potential can be different. The linear term which we would not be able to interpret has gone away, and in the quadratic terms, which are the mass terms, you can see that m of phi 1 not equal to 0, but m of phi 2 is equal to 0. So what has happened now? When I break a global continuous symmetry, I get one massless boson when I reinterpret in terms of the dynamical fields, and one massive boson. So here I have, let me write it down here. This is called the Numbu Goldstone theorem. So, when I break a continuous symmetry is spontaneously broken, there exists a massless boson in the theory, and this is called the Goldstone boson. Is it clear? So, let me recap what we have done till now. I took a Lagrangian which had a U1 global discrete symmetry due to a real scalar field, and when I take m squared less than 0 and ask what it means, I find that I can rewrite it in terms of physical dynamical fields which, or phi, which has a mass non-zero and positive definite. M squared was positive definite, square root of minus 2 small m squared, and therefore it was a well defined theory. However, in redefining these fields, because we had to choose a particular ground state, the ground state broke the invariance that the Lagrangian has. Please understand, remember, the Lagrangian still carries this invariance. The Lagrangian is still invariant under the symmetry, the ground state is not. We have not actually added a term which explicitly breaks that invariance, because at the Lagrangian level the theory is still invariant. Hence the theory is called spontaneously broken. We do not break it, it is breaking by itself. Is that statement clear? What spontaneous is doing? Spontaneous means by itself. So, by itself the theory breaks the symmetry because of the choice of the ground state, which is forced upon us because ground state has to be unique. Okay? Now, I do the same thing with a global continuous symmetry. So, I have a ring of ground states, or rather ring of minimum energy solutions. Again, I have to pick one of them as the ground state, and when I do that, one particle gets a mass, the other particle does not. Now, the reason is actually here I chose the phi 1 field to be the vacuum non-zero vacuum expectation value field, and the phi 2 to be the one which has 0 vacuum expectation value, but I can always write it the other way around. I could have put m1 equal to 0 and m2 not equal to 0. There will be one massive and one massless field, okay, in this case. So, there is another physical and this goes by the name of a theorem. Of course, if there are n number of symmetries, you can count how many massless bosons there are, okay, there will be more. So, for every symmetry that is spontaneously broken, you will have continuous symmetry that is spontaneously broken, you will have one massless boson. Ask the question.
Ma'am, I am still not able to get the point that you are talking about continuous symmetry is broken.
Here, so let me ask, so here is, let me write it in a different way. Here is my phi 1, phi 2 field. This is a circle of radius v. That means phi 1 squared plus phi 2 squared is equal to v, which was, you remember, minus 6m squared by lambda, right? I am not changing that. Every solution on this line is a minimum energy solution, because that minimizes the potential and therefore it minimizes the Hamiltonian, right, and therefore the energy is minimum. Okay, I have chosen to expand my theory around this point as the ground state. I took phi 1 is equal to v square. Okay, I could have chosen any solution. By the way, you can do this as homework, maybe I will give it to you as an assignment. Okay, you can choose anything. I could have chosen this point, and still the dynamical content of the theory will be the same, one massive and one massless field. Is it okay? So, let us try to understand it in a different way. What do you mean by saying that there is one massive and one massless field? Let us look again at this thing. Suppose these are components of a charged scalar field phi. Suppose I write this field as in terms of r theta component. So, I can write it as phi r e to the I phi phase. So, there is a real component and a phase component, And when the phase component is small, I can write this as 1 plus I phi, which is phi r plus I phi prime, which looks like this, right? Is it clear? Now what happens is this. Let us look at this field over here. This is the circle of minima. So this is the continuous symmetry, right? Because I can choose any point on this circle to be my ground state. Okay? In the earlier case, when I had only one phi field, I had only two solutions. That was my discrete solution. Here I have a continuous solution. So the way to look at it is this. Because of this relationship, you can see that phi 1 being non-zero is like phi r having a non-zero vacuum expectation value, while the phase term has a zero vacuum expectation value. If you go back to this, it's like this. What do I mean by saying that I am writing the dynamical field phi tilde as some, or I am writing the field as some phi naught plus a dynamical component, right? This means that this actually corresponds to fluctuations around the minimum. So let us fluctuate these two around the minimum. Let us look at it in terms of the real and imaginary part. What happens when I am changing phi r? Phi is the radial field. So when I am changing phi r, I am going either to this side or to this side of the minimum. If I am changing the phase, I am going along this line. So I am actually going on the circle. When I am going on the circle, when I am when I am making fluctuations of the phase, when I am going on the circle, I am meeting other points all at the same energy. So it costs no energy to go in the phi 2 or the phi prime direction. But if I am going off the minimum, then it costs energy, because this is the potential minimum. If I go off the minimum in either side, I am going to a higher potential state, therefore it costs energy, and therefore you can think of phi 1 as having a non-zero mass and phi 2 having zero mass.
So, ma'am,
Yeah.
instead of saying there is 1 degree of freedom of massless and one of massive, you should, I think you should say that there are 2 degree of freedom of massless and 2 degree of massive.
No. These now phi 1 and phi 2 are real. Please understand. Phi 1, phi 2 are real. Okay. So there are 2 degrees of freedom. So phi dagger are the complex fields, and they can be written in terms of 2 real fields, right? The degrees of freedom never change. You have to count it correctly. So this is 2 real fields or 1 complex field, and this is 2 real fields, 1 massive, 1 massless. Degree of freedom hasn't changed. It's just that if I write a Lagrangian which looks like a Klein-Gordon Lagrangian but with negative mass squared, then physically the content of that theory actually is 2 scalar fields, Klein-Gordon proper scalar fields, one which has a mass, one which doesn't have a mass. Is this clear? Yeah.
Ma'am, I want to just ask that if your particle is move on this circular line, circular line, so it is massless degree of freedom because there is no energy dissipation.
Correct. Correct.
Okay, so there are 2 directions for motion of in this circle. Either
if you look at it in this way, yes. If you look at it in this way, yes.
So that's the way I'm talking about. There are two directions for particle to move
Yes.
in a massless degree.
Yeah, but each is 1 degree of freedom. There are not 4 degrees of freedom, right? It's a scalar field. It's only 1 degree of freedom, that's all. So 1 degree of freedom is phi r and the other is phi prime, or it is phi 1 and phi 2. Whichever way, there are only 2 degrees of freedom. This is not a vector, this is a scalar quantity, right? So each object has 1 degree of freedom. So what you thought was a 2 degrees of freedom phi 1, phi 2 with negative mass squared, that is a spurious definition. The dynamical correct way to understand it is still 2 degrees of freedom, one massive and one massless. Okay? And just look at the math, right? I have a feeling there's a mistake here because the mass should have been same minus 2m squared. So maybe I made some mistake here, but certainly 0 is 0. That's all I wanted to show you. Okay? Is it clear? Yeah. Yeah.
So the continuous symmetry in question is the symmetry of the Lagrangian or the symmetry of the ground. For example, if
The statement is always this, when it is broken at the ground state level. The Lagrangian, go back to the Lagrangian. See, whether I write the Lagrangian in terms of phi 1 field or phi 1 tilde field, it's the same Lagrangian, right? Because it's simply a redefinition. The redefinition allows you to understand the dynamical content of the theory. But the Lagrangian hasn't changed. Since the Lagrangian was symmetric with respect to phi 1, phi 2 fields, it is remaining symmetric throughout. It is that the choice of ground state is forced upon us, and that breaks the symmetry at the ground state level. This is a very important consideration. See, okay, maybe I will tell you a little bit fast forward what will happen. If you remember, you had a J mu, so let me just go to a little bit what we had past and little bit future. You remember that we had J mu for the weak field, okay, was psi bar gamma mu 1 minus gamma phi psi prime. For example, maybe I will just write J mu plus, I don't remember whether it was plus or minus, maybe nu bar E. This is psi nu bar and psi E, okay. Now I wanted d mu J mu, so maybe I put d mu J mu plus must be equal to 0, but that actually gave you, was actually of m nu minus me, so this is, yeah, times nu bar L gamma mu EL, right, and not equal to 0. So if I put explicit mass terms in the Lagrangian, then I don't even have my global SU2 symmetry, leave alone my local SU2 symmetry, okay. Now what I am going to do, you see, I am going to maintain the symmetry at the Lagrangian level. That is, I am going to keep this massless, so that my theory is invariant under SU2, U1, whatever. We will make sure that it is locally and globally invariant under those transformations, under those symmetries. But we will introduce the mass through coupling to a scalar field, and that is exactly what I am going to do next. Okay. So somebody needs to mute. Yeah.
one real field that a discrete symmetry.
Just one moment. Somebody please mute.
Please mute your mic.
Okay.
And what we saw was that for the real scalar field, we had a discrete symmetry.
Yeah.
And for the complex 2-degree field, we have a continuous symmetry.
Yes. 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 Continue. I will just write it down so that you can see. Okay, I have just written the summary of what we saw. Is it clear? I mean, positive meaning, I mean, 0 is also positive, right? So both are positive mass squared, but in particular, one is massless. Okay? Okay. Now what we are going to do is that we are going to take this field, we are going to take this complex field. So same complex field. So this was all under global U1. This was global U1. Now I am going to couple it to, so I am going to ask local U1 implies I want to couple this to some gauge field, right, using my J dot A interaction. Let me call it J dot B, some U1, it is not the electromagnetic U1. And let us see what happens. So let me actually tell you what will happen before I do the calculation. So what will happen is that I have this scalar field has if I don't have the interaction with the gauge boson, then I have one positive mass squared and one massless field. Now what happens is that I couple it to a J dot B where there was no mass term. I have my whole Lagrangian has every field massless. What will happen is that this, therefore, this B field, what does it mean to be massless? It has only transverse degrees of freedom, right? 2 transverse degrees of freedom. Now what will happen is that this massless field will couple with these 2 transverse degrees of freedom and it will give you a massive B field. Is it clear? So this is what I am going to show you now. It will take few classes, we will do step by step. So all I want you to understand is that this Goldstone boson is a problem for us because no massless scalars have been seen in nature. See, anything massless is so light it is going to be easily produced because it is massless. But nobody has seen a massless scalar. I mean, you have seen a pion which is very light, but it's a pseudoscalar. Here we need a scalar, not a pseudoscalar. Nobody has seen such a scalar, so it should not exist. But if you couple this to your B field, then what happens is that this massless degree of freedom becomes the longitudinal component of this vector field and gives you a massive vector gauge mediator field. So that is what we are going to see now. So what will I write now? Let me write my Lagrangian. So I am not going to do the scalar field part. The scalar field part I have already done. So we will again get phi 1 squared plus phi 2 squared is equal to v squared is equal to minus 6m squared by lambda. All that is the same. I will again choose phi 1 to be the field which gets a non-zero vacuum expectation value. I will rewrite in terms of phi 1 tilde, phi 2 tilde. All that part will be the same. Now what I am going to do is, since it is a local u1 invariance, I have to replace my ordinary derivative by my covariant derivative. So now I will bring back the d mu phi dagger, d mu phi term. Or let me just call it. So this v of phi term, all the analysis will give you this portion. Okay, is it clear? So I am only going to look at this portion here. So what will I write? Now L local will be d mu phi dagger d mu phi minus v of phi, where let us now take some u1. So let me consider a generic local u1 gauge transformation, so that phi prime
Ma'am, your V5 will also be changed, right?
Sorry? No,
phi
phi.
will also be changed.
Why? It has done no coupling to the electromagnetic to the u1 gauge field, right? V phi only has m squared phi squared and lambda by 4 phi 4 lambda by 4 factorial phi fourth, right? So V phi doesn't know anything about, V phi is the potential for the phi field. He doesn't know anything about.
It won't change. The form is psi star psi. So
Let me write V of, can you see this part of the board, is equal to m squared phi dagger phi plus lambda by 3 factorial phi dagger phi whole square. So there is no smell also of gauge field over there, right? It is purely phi field.
I was just thinking that when we change the normal derivative to covariant derivative,
That's what we have done here.
Lagrangian, we will often add terms like 1 by 4 f square.
Yeah. That we will do. That will not. See, this is the theory that will let's call it G mu nu. This is not going to bother us. This is the kinetic energy term of the gauge field, right? This is the potential of the phi field. I am only interested in seeing how the phi field couples to this field, right? This will not change. This has nothing to do with the phi. This is phi independent and this is B independent, right? I am only looking at the coupling over here. I only want to look at how it couples to this. I want to couple this to some gauge field and I want to look at that J dot A interaction which is sitting over here and see what happens to this, okay. So I put some generic coupling d mu plus Ig b mu. So now let me look at d mu phi is d mu plus Ig b mu and phi is, sorry, phi 1 plus I phi 2 by root 2, right? And for phi 1 I am going to write phi 1 tilde plus V plus I phi 2 by root 2. So now let me write that down. So let me write d. So let me first take d mu acting on all these things. So it's d mu phi 1. So d mu V will be 0 plus I d mu phi 2, then plus Ig b mu phi 1 plus I g b mu phi 1, then plus IgV b2 plus IgV b2, sorry, b mu, then minus G b mu phi 2, and I am going to write d mu phi dagger d mu phi, right. So I have written it as A plus IB mod squared, right. So this will be A squared plus B squared. So it will be d mu phi 1 minus G b mu phi 2 squared plus d mu phi 2 plus G b mu phi 1. By the way, phi 1, phi 2 must all be tildes, but I am just, because we have no non-tilde fields, plus G v b mu squared. So you can see that I have terms which look like d mu phi 1 squared, d mu phi 2 squared, and then I have forgotten the root 2, so there is a half everywhere. I noticed that because I have to get half d mu phi 1 squared plus half d mu phi 2 squared, okay. Then the square of this is phi 1 phi 2 b term, that is the interaction term between phi 1 phi 2 and b, right. So let me write that minus 2, so 2 and 2 will cancel, so G d mu phi 1, I am going to drop the tildes, okay, phi 2, then I have to square this, so I get plus G squared b mu squared phi 1 tilde squared. I have to square this. So you look at this very carefully. So this is the term of interest. Please look at it carefully. So I have squared this. Now I have to write the cross terms plus 2. I'll write it here. Plus 2 G b mu phi 1 d mu phi 2 plus 2 G v b mu d mu phi 2 plus 2, no, there won't be 2 because there is a half, right, there is a half outside, so no half, G squared b mu squared phi 1. Okay, so this is the kinetic energy term phi 1 we understand, kinetic energy term phi 2 we understand. Now this is an interaction of 3 fields, so it's some interaction term. This is an interaction term of 4 fields, so this is an interaction term. Now look at this term. What is this term? Yes, so this is the mass term, half mass of the B squared, B mu, right? So that means the B field has acquired a mass GV, okay, and it depends on the vacuum expectation value of the phi field, because V is the, so G is the coupling of the coupling to that whatever interacting gauge mediator field, and V is the vacuum expectation value of the phi field, and the combination gives you the mass of the B field. But we are still not finished. Why are we not finished? So this is cubic coupling, this is a cubic coupling, but this is a problem. Why is it a problem? Because this is a quadratic term, only B and phi. We don't know how to interpret this. So we have a tantalizing glimpse of something which looks like a mass term for the B field, but we have a term which we cannot interpret. The other terms are all fine. So what we will do is that when we interpret this field, in the next class I will continue, what will happen is that this term and this term all go into giving the correct mass term for the B mu field, and only the kinetic energy term of phi 1 will be left. So there will be no propagating phi 2 field. Instead there will be a mass term for the vector boson. Is this clear? So this is what spontaneous symmetry. So you can see, now you understand what I meant by saying totally bizarre, why it had to be done this way, but it gives the right answer. Okay, so I will make some more remarks after I complete the calculation next time. Okay, so I will stop here, but now you see that step by step what we have seen. For some reason we don't know, we take the mass square to be negative for some scalar field with a phi 4 interaction, and if it has a continuous symmetry and you break it globally, you get one massive scalar and one massless Goldstone boson. And if you couple that field to some massless gauge field B, then we will find out that the phi 2, the massless Goldstone boson, completely disappears. It has to disappear, that is why I have kept d mu term over here. It completely disappears, and instead you get a massive gauge field. But since everything here is simply a rearrangement of the already existing fields, the original Lagrangian still satisfies or respects that local gauge invariance. This is the most important part. Okay, we have not lost that gauge symmetry. What has happened is that the ground state does not reflect that or respect that symmetry, and we have spontaneous symmetry breaking. But on the plus side, we have therefore managed to give masses to this gauge boson without breaking that invariance, which we could not have done if we had put explicit mass terms in the Lagrangian. Is this clear? Okay.
And this B mu field has 2 degrees of freedom, right?
Yeah, 2 transverse degrees of freedom. Now it will get the third.
Yeah, so it will have 3 degrees.
It will have 3, and that's a massive field. Yeah, so any massive field will have 3 degrees. It will have a longitudinal plus 2 transverse polarizations, right? So it will be a proper massive field, and that's the mass. This mass will remain. This we will have to reinterpret. That's all. Okay, GV will be the mass. So I will tell you physically what it means. Okay, then what we will do is we will go to the full electroweak SU2 cross U1 theory and give masses to all the. So we have to give masses to W and Z bosons, which are different from each other, and we have to make sure that the photon remains massless. So that will be the next step. So first, next step will be to understand this so-called unphysical looking terms. Then we will repeat the whole thing for SU2 cross U1. This is all only U1, right? We will do it with the whole local SU2 cross U1 symmetry, and that will give us the complete content of the standard model. There will be some more terms to add for the masses of the fermion fields, which is completely ad hoc. We will do that in the end. Okay?
Yeah. This part, where can we find this part?
It should be there in Halzen. It should be there in Halzen. I will look. Yeah, I will look in the book. I didn't bring it with me here, so if it's not there, I will tell you where it is. It should be there anywhere. I mean, you can look at Idziksen. It should be there in Idziksen. I'm sure Peskin should have it. Oops, sorry.
It's there in Rider as well.
Yeah. Any field theory, any standard field theory textbook will have it. So Rider, Bjorken and Drell, Idziksen, Zuber, Peskin, anyone will have it. Okay, so you can look at it.
Presentations, ma'am, they're going to be like what is the duration for each presentation?
So there are 10 of you, right? That's what I said. If you take 1.5 hours and split between 3 or 4 of you, right? I mean, you should take 20-25 minutes max, right?
Yes.
All right? I mean,
Yes, ma'am.
because I think you'll need that much time. See, if you're writing it on the blackboard in front of all of us, it can go faster. But I think that by the time you people, upload the thing and display it and all that, it will take time. So I don't want to, cut it shorter than that.
So, ma'am, it will take at least 3 classes.
Yeah, it will take at least 3 classes. Yes, it will take at least 3. I might ask you for one extra class somewhere so that we can finish it off. Okay, I don't need many more classes. Once I'm done with spontaneous symmetry breaking and giving masses to the gauge bosons and then to the fermions, I'll essentially stop there because we have built up the whole theory. And as I said, I want one last class to make a few remarks.
And so we mail you about the topics that we are going.
You were supposed to have done it by last Tuesday.
No,
Please do it. Please do it. Okay. I always feel when you don't send it to me that you have sent it to Prabhat. So I have not checked with him. So please be sure that all of you have sent your topics, because by this weekend you should even send in the write up, right? So please make sure that you don't waste more time. Okay. So there are, as I said, there can be a lot of conceptual doubts about this, but at least mathematically you have seen what the pattern is, right? Is it clear to everybody? Can we stop here?